In this session, we are actually going to talk about the power series method. In our previous session, we covered the basics of the power series method. Okay. So we are going to start this session by stating yet another theorem, that is the power series solution theorem. This theorem will be applicable to differential equations of second order with variable coefficients. Okay. However, we are going to discuss only the homogeneous differential equations. Okay, because once we get the homogeneous ODEs, we can use the variation of parameters method to get the YP. Okay, so we will only be focusing on finding YH now. Alright. Now in almost all of the differential equations that we will be solving with the help of the power series method, they will involve the coefficients. Okay, let us recall the standard form: y double prime plus p of xy prime plus q of xy equal to 0. Okay, so the coefficients that are involved are either usually constants or rational functions. Okay, so we will discuss the significance of the singular points of the rational functions as far as the power series solution theorem is concerned. And once we do that, then we will see an example, okay, of solving a differential equation of this kind by the power series method. And I think you should note the steps that we are going to follow very carefully while we solve this particular problem. Okay, and then we'll talk about the interval of convergence theorem, or what's the significance of R of the Taylor series of the coefficients. Okay, so we are also required to use the Taylor series or the Maclaurin expansions of P of x and Q of x. Okay, so let us start. Okay, the power series solution theorem. This theorem requires us to have a second order ordinary differential equation of the form d2y by dx squared plus p of x into dy by dx plus q of x into y equal to 0, where p of x and q of x can very well be constants. Okay, but in their most general case, they are functions of x only. Okay, and it is known, or it should be known, that p of x and q of x are analytic at x0. And for us, what is the definition of analyticity of any real variable function at a point? The function should be defined, so are its derivatives. Okay, also all the derivatives of the function should be defined, so we'll have a convergent Taylor series, okay, or power series. So what is the conclusion of this theorem? If we have an ODE of the form of this form and p of x and q of x to be analytic at x0, then the conclusion is that every solution that we get, or we may get, of the ODE is analytic, meaning it will have the solution as well as its derivatives all will exist. And second thing, the radius of convergence, because the solution that we are going to get is going to be in the power series form, so we have to talk about the radius of convergence. Okay, so the radius of convergence of every solution is at least as large as the smaller of the radii of convergence of the Taylor series expansions of either p at x0 or q at x0. Okay, so let us just reread the theorem. Okay, so we have an ODE, and throughout our discussion we will be talking only about this ODE. For this theorem, we have both p of x and q of x to be analytic at x0, and according to the theorem, we conclude that every solution of the ODE is going to be analytic, and because it is a power series solution, it is essential to talk about the radius of convergence, and the radius of convergence of every solution is at least as large as the smaller of the radii of convergence of these two Taylor series expansions. Of which two functions? Of the coefficients p of x and q of x at the point where both p and q are analytic. Okay. Now, as far as the rational functions are concerned, if our differential equation consists of coefficients which are rational functions, then we know that they will be singular only at those points where the denominator is 0 and the numerator is non-zero, assuming that the common factors have got cancelled. Okay, and in such cases, how are we going to determine the radius of convergence of expansions of p and q? It will be the distance between x0 and the nearest 0 of the denominator. Okay, so let me give you an example. Suppose our function p of x is this function 1 upon x plus 2 into x squared plus 1. Okay, now clearly this has only one real 0, the denominator, and that is x equal to -2. Okay, but it turns out that this particular denominator also has two more zeros which are complex, okay, which are purely imaginary, plus or minus I. Okay, so if I were to show these three zeros on the complex plane, okay, then plus I and minus I will be sitting here, and the 0 minus 2 will sit here. Okay, so actually the radius of convergence is not equal to 2, but it is actually equal to 1. Okay, because it is the nearest 0 of the denominator, which is not minus 2, it is I. Okay, so the circle of convergence, I would say, or the region of convergence is going to be the unit circle. Okay, or R will be equal to 1. Okay, so although on the real axis this particular function has a 0 at -2, okay, due to the non-real zeros, okay, the radius of convergence is now not 2 but it is 1. Okay, fine. So this is the power series solution theorem. Let us now see how we apply this theorem with the help of an example, and there we will encounter the rational functions. Okay, so this is the question. We are going to solve the initial value problem consisting of the second order differential equation x minus 1 into d2y by dx squared plus dy by dx plus 2 times x minus 1 into y equal to 0, with y4 given as 5 and the derivative's value at 4 is 0. Okay, and we are required to solve it on the interval closed at 4 and all real numbers greater than or equal to 4. Okay, the very first thing that we should do here is we would like to write down the given ODE in the standard form. Now what do we mean by the standard form? It's the one stated in the theorem, y double prime plus py prime plus qy equal to 0. So we have to divide the differential equation by x minus 1, the coefficient of y double prime. It should always be 1. Okay, so this is going to tell us the functions p of x and q of x. Okay, p of x is going to be 1 upon x minus 1 and q of x is going to be 2. Okay, very simple. Second thing is we should identify the singular points of p of x and q of x. Okay, fine. So let's first talk about q of x. Okay, now q of x is a constant function 2 because it already had the factor x minus 1 which got cancelled. So will this have any singular point? No, none of them. Okay, But as far as p of x is concerned, which is 1 upon x minus 1, there is one singular point, that is x equal to 1. Okay, so if we wish to apply the theorem, okay, we cannot choose the point of expansion to be 1, okay, because for this for the applicability of the theorem, or for the validity of the theorem, both p and q should be analytic at x0. But here in this example, the first function is not analytic at x equal to 1, that is p. So if at all we want to choose any point or any number, the center, we cannot choose it to be 1. Okay, but because we are already given these initial conditions, y and y prime at 4, let's make the choice of x0 as 4. Okay, so we will find the power series solution in terms of the powers of x minus 4. Okay, yes, so the third step is actually making a choice of the point of expansion x0. And the thing is, according to the theorem, both p of x and q of x should be analytic, and if x0 is already given and is not equal to the singular point, we choose it. Okay, see, don't be under the impression that we cannot actually expand it if the point about a singular point. Okay, we actually do it in the next I would say next variant of the power series method, which is called as the Frobenius method. Okay, remember when we studied the functions of complex variables, we did have the Laurent series expansions. Okay, so where the function was not even defined at that particular cent. Okay, so coming back to the choice of point of expansion, because x0 or because the values of y and y prime are given at 4, let's choose x0 to be 4. Okay, so now what we will do is we will get p of x and q of x, if possible, in terms of the term x minus 4. Okay, so we'll perform our usual manipulations, bring in x minus 4 here. Okay, so we'll subtract and add 3, and then we'll take 3 common, so it will then be this particular geometric series. Okay, 1 upon 3 into 1 plus x minus 4 upon 3, or 1 upon 3 into summation as n goes from 0 to infinity, minus 1 raised to n into x minus 4 upon 3 raised to n. Okay, because we would like it to be in the form 1 minus 1 upon r, 1 plus r squared, and so on. Okay, and where does it converge? It converges when the absolute value is less than 1. Okay, we very well know this result. All right, so the rewriting of p of x in terms of the power series allows us to find the least possible radius of convergence r. Okay, what is it? It is predicted to be the distance in the complex plane from x0 to the nearest singular point of p and q. Okay, q doesn't have any singular point. In this example, p does have one singular point, which is the real number 1, right? So the least possible radius of convergence is going to be the distance between x0, which is 4, and the nearest singular point is 1. Okay, so the radius of convergence is 3. Okay, so this means our solution will be valid in the region mod of x minus 4 less than 3. Okay, or when x lies between 7 and 1. Okay, see, now the significance of the fourth point is here. Look at the second point. The radius of convergence will be the distance between x0 and the nearest 0 of the denominator. Meaning, if p of x were in this form, will you consider r to be 2? No, you will not consider r to be 2, because in the complex plane, we do have additional zeros of the denominator which are closer to the point of expansion, okay, or 0. So you will then choose r to be 1 and not 2. Okay, So please be very careful. So having identified the least possible radius of convergence, in this case it is going to be 3 units, it's now time to bring in the power series representation of y, okay, or the unknown function. So once we get the coefficients a n, our job is done. Okay, so let us assume that y is in the form summation as n runs from 0 to infinity a n multiplied by x minus x naught the power n, and from this get y prime and y double. Okay, now this is a common step among all problems. Okay, x naughts may be different, but you have to be very good at well, even if you already know y prime and y double prime by the power series manipulation theorems, nothing like it will save your time. Okay, but because now we are doing it for the first time, let's just follow the process. Okay, so assuming y to be in this form, the power series form, apply the term by term differentiation. Okay, so y prime will be summation as n runs from 1 to infinity. It won't be 0 now because a naught is 0. The derivative of a naught is 0, so it will be summation n running from 1 to infinity a n into x minus x naught to the power n minus 1, term by term differentiation. Okay, and because our differential equation also has the second derivative, let us differentiate y prime term wise. Okay, so summation as n running from 2 to infinity a n into n minus 1 into x minus x naught to the power n minus 2. Okay, now how are we doing this? We are doing this by taking the help of power series manipulation theorem. Okay, which we have seen in the previous session. Okay, now our next job is, and this is the crucial step, we have to change the dummy indices or dummy variables and the lower summation limits. We have to change them and combine the sums into a single term, and this is what we did when we solved the problem dy by dx plus y equal to 0. Okay, fine. So to achieve this, and this is the crucial step in the entire solution, even if something goes wrong here, your coefficients will be different. Okay, the first step is we have to put y prime and y double prime, which we obtained here, in the original differential equation. See, now this need not be in the standard form. Okay, in fact, if it is in the standard form, then the calculations may become difficult. Okay, so let it be in the original form, x minus 1 y double prime plus y prime plus 2 into x minus 1 into y equal to 0. But while putting y prime and y double prime, you please make sure that all the remaining terms are also in the powers of x minus x naught, or x minus 4 in this case. Okay, so wherever you have x minus 4, please write wherever you have x minus 1, you please write it as x minus 4 plus 3 or 3 plus x minus 4. Okay, so let us now start with the first term. Okay, here we have x minus 1. Okay, write it in terms of x minus 4, so it will be 3 plus x minus 4. Okay, second term, okay, let me write it using the Roman 1, y double prime. Have we already developed an expression for y double prime? Yes, it is. Okay, put it here. Okay, see, now it's not very difficult to write a n into n minus 1 into x minus 4 to the power n minus 2. The most important thing here is the lower limit on n. Okay, fine. Now let us go to the next term, which is y prime. So let's use the Roman 2, a n into x minus 4 to the power n minus 1. This is the summand. Limits are limits on n are 1 to infinity. Okay, again note that a naught is 0, so we can write it as from 1 to infinity. Okay, then let us go to the term 2 times x minus 1. Constants will be there as they are, so As far as x minus 1 into y is concerned, rewrite it as 2 into 3 plus x minus 4 and into y, the third term here. Let us write it as summation an into x minus 4 to the power n as n runs from 0 to infinity. Okay, fine. So what we have now done is we have written everything in the differential equation in terms of powers of x minus 4, because 4 is the center of the power series solution that we have chosen. Okay, and of course the right hand side is 0. Okay, it's not going to change. Now for simplicity, what we will do is we will assume that x minus x naught is z. Okay, and don't assume it to be y, because y is the dependent variable. Okay, and also z is not any complex variable here. Okay, z is simply the real variable. Okay, x minus 4. Okay, fine. So let me write it here, z equal to x minus 4. Now this is going to simplify our task of writing x minus 4 every time. Fine. So we will now multiply the sums by these coefficients. Okay, so we'll multiply the y double prime's power series representation by 3 and x minus 4 separately, and we will do the same thing for this. Okay, so currently we are having 3 terms added together on the left hand side, but at the end of the multiplication step we will have 5 terms. Okay, this term will remain intact. Due to the first term we will have 2 terms, and due to the last term we will have 2 terms. Okay, so let us start multiplying. First let us multiply y double prime by 3. I have taken that 3 inside. Okay, so 3 times n into n minus 1 into z to the power n minus 2, where z is x minus 4. Okay, now let us go to x minus 4. Let me use green color. So when you multiply the y double prime by 3, you get this. Now let us go to this x minus 4 into the y double prime. Okay, so what change will take place now? This power n minus 2 of x minus 4 will increase by 1. Okay, and it from n minus 2 it will become n minus 1, isn't it? Because we are multiplying by x minus 4, everything else inside the summand is not going to change. Okay, so same limits, an into n minus 1 into x minus 4 or z raised to n minus 2 plus 1 or n minus 1. Okay, don't disturb the third term, keep it as it is, because it doesn't have any coefficient, okay, to be multiplied outside the summation. The only thing that will change here is x minus 4 will get replaced by z. Okay, fine. Now let us go to the last term. Here we have 2 outside, so if we multiply the y series by 3 and then by 2, then it will be 6 times a. Okay, there, so limits end 0 to infinity, 6 times a n into z to the power n. Then let us go to the next term here. So like in the first term we have the power of x minus 4, but also let's not forget 2. Okay, so in the last term that we are going to write, we will not only have 2 accompanying an inside the summand, but the power of x minus 4 will now be n plus 1. Okay, because of this additional power. So in the z notation it will be z to the power n plus 1. Don't change the right hand side, let it be 0. Okay, so let me explain you this step once again. What we have done here is we have substituted y prime and y double prime in the ODE. We have kept it in the original form, and all terms have now been written in terms of powers of x minus 4. Okay, then we have brought everything inside the summation notation, resulting into these 5 different sums. Okay, let me call them A, B, C, D and E. Okay, now eventually we would like to represent the sum of these 5 sums as a single series. Okay, but for that we need to take care of the fact that the summand in all 5 should have the same power of x minus x naught. Okay, let me explain this. Observe that in A, in the sum A, we have got z raised to n minus 2. Yes. In B, we have got z raised to n minus 1. Same thing with the third one. In the fourth, now this is better because we have z to the power n, and here we have got n plus 1. Okay. So out of these 5 sums or 5 terms, the only term that is d, which is in the desired form. Okay, z to the power n, where n is the summing variable. Okay, so what we would now like to do is we would like to introduce 3 new summing variables temporarily. Okay, to take care of n minus 2, we will assume that n minus 2 is m. Okay, to take care of the summands in B and C, we will substitute n minus 1 as L, and to take care of the summand in the last term, that is z to the power n plus 1, we will let n plus 1 to be S. Okay, so what this does is, if we go to the next step, due to the substitutions of n minus 2, n minus 1 and n plus 1, all 5 sums A, B, C, D and E will have the variable, the summing variable to be the power of z. Okay, you may see that now. For A, it has now become z raised to m. Okay, because we have substituted n minus 2 as m. For the terms B and C, because we have substituted n minus 1 as L, it is z to the power L and z to the power L. Okay, and for D, nothing is going to change obviously. But for the last one, what will change is n plus 1 will change. Okay, we have to write it as S. But now this has created a problem. Okay, because we have n as subscripts of the coefficients, as well as there are n functions of n present here, n into n minus 1. Okay, so we will now change these subscripts as well as the n terms and the n minus 1 terms. Specifically, if we go to the term A, okay, where n minus 2 is m, then n will become m plus 2. Yes. Okay, so if we have a n there in A, it will be now a m plus 2. So clearly n into n minus 1 will become m plus 2 into m plus 2 minus 1, or m plus 1. Okay, into z raised to m. And let us also talk about the limits now. Okay, in the original sum A, the limits on n were 2 to infinity. We are now letting n minus 2 to be m, so the lower limit on n will be 2 minus 2 or 0. Okay, upper limit obviously is going to be infinity. Okay, so as far as the discussion is concerned regarding the sum A, we are done. Let's go to the terms B and C. Okay, now here what we have is n minus 1 being put as L, so n is going to be L plus 1. So wherever we have n, we will replace n by L plus 1. Okay, so this is n, it will get replaced by L plus 1. N into n minus 1 will be L plus 1 into L plus 1 minus 1, so it is going to be L plus 1 into L. Now I have highlighted this L because it is going to play another role, okay, as far as limits are concerned. Okay, into z raised to L. Now let's talk about the limits in the term B. Okay, n is starting from 2, L is n minus 1, so L will start from 1. Okay, yes, so this is as far as the term B is concerned. Let's go to the term C. N will get replaced by L plus 1, so an will be al plus 1, and we have this n which will get replaced by L plus 1. See, now the only difference between the sums B and C is in limits. Okay, in B, lower limit on n is 2, but here the lower limit on n is 1. Okay, and we saw in B that the limit got decreased by 1 due to the substitution n minus 1 equal to L. So if n is 1, then n minus 1 will start from 0. Okay, so we have now successfully completed the conversion in B and C. Let us now go to E. There is no need to touch D now. Okay, well, it is a very good term. Okay, let's go to E now. In E, we have n plus 1 being substituted as S. Yes, so obviously if n plus 1 is S, then n is going to be S minus 1. So this n will become S minus 1. Z to the power S will be there as it is. Let's now talk about the limits. Okay, unlike the first terms, here the lower limit is going to increase by 1 because we have substituted for n plus 1. Okay, so if n is 0, then S, the lower limit on S will be n plus 1 or 1. Okay, so in this step what we have done is, in all the 5 summands, the variable of summation itself is the power, and this is important. This is going to help us a lot. Okay, in fact this is the standard process. Okay, now having converted every summand in the powers of Z, in the powers of the summing variable, let's now start to think about the term by term addition or term wise addition of the terms. Okay, in these 5 sums. Now the problem is the limits. Okay, the lower limits in these 5 sums are different: 0, 1, 0, 1, 1. Okay, so we would like to now focus on B and E. Okay, why B and E? Because as far as A, C and E are concerned, A, C and D are concerned, the lower limits are 0, M0, N0 and L0. Okay, so let us now go to B. Okay, let's now ask this question: if we let L start from 0, okay, will the summand be valid? It will be valid because of this L. Okay, so because of this L, even if we let L start from 0, due to this L, the first term is not going to play any role. Okay, it is still going to be 0. So due to the L term highlighted and encircled in the green color, we may let L to change from 0 to infinity, including 0. Okay, now let us go to S5, okay, or E, this one. Now here we have to assume that A minus 1 is equal to 0, only then we can start from S equal to 0. Okay, so this assumption is crucial, and well, we let it be. Okay, we assume that A minus 1 is equal to 0. Now, having achieved what we wanted, that is 2 things. First, writing down the powers of the x minus x naught term or the z term as the summing variable, first objective. Second objective is we have achieved we have obtained the lower limits of all 5 sums to be zeros. Okay, so now it's the right time to change the summing dummy variables back to n. So n is going to be our new summing variable, and lower limit on n has to be 0, and that's why we did all the things that we did in the previous step. Okay, which is now going to result into this particular infinite series. Okay, so pay attention. Now M, L and S, everything will get replaced by n. Okay, and because z raised to m, z raised to l, z raised to l, z raised to n and z raised to s are present in A, B, C, D and E respectively, using the manipulation theorem, power series manipulation theorem, we can now take z raised to n outside. Not outside the summation, of course, inside the summation, but outside the coefficients. Okay, now let us start writing down every coefficient. Okay, go to A. What is the coefficient? 3a m plus 2 into m plus 2 into m plus 1. Put it here. 3 n plus 2 into n plus 1 into a n plus 2. Done. Go to B. Okay, a l plus 1, a n plus 1, l into l plus 1, n into n plus 1. Done. Go to C. Okay, in C we simply have a l plus 1 into l plus 1, a n plus 1 into n plus 1. C is done. D, the nicest of all, don't do anything, let it be 6 a n. Okay, now go to E. Okay, z raised to n has already been taken outside, so it is going to be 2 times a n minus 1. E is done. Now again, by the application of the theorem, let's not apply it right away. We would now like to combine these. Okay, observe that a n plus 1 is present in 2 different terms. Okay, so if you take a n plus 1 common and identify the coefficients, which are n squared plus n and n plus 1, that will be n squared plus 2n plus 1. So you may combine these two terms as n plus 1 the whole squared into a n plus 1. Okay, and now apply the theorem. Okay, term wise manipulation theorem. If you have two power series which are identical to each other, then all the coefficients must be equal. Okay, so this is what we get now. Okay, we are now required to take this particular expression involving the coefficients and n and equate it to 0. Okay, so if we do that, then we'll get what we call the recurrence formula or the recursion relation. Okay, by setting the coefficient of x minus x naught in the sum to 0. And why are we allowed to do that? By the manipulation theorem. Okay, the third conclusion that I told you. Okay, so this is now going to get the following recursion formula: 3n plus 2 into n plus 1 into a n plus 2 plus n plus 1 the whole squared into a n plus 1 plus 6 a n plus 2 a n minus 1 equal to 0. Okay, now what we usually do is we look for the largest subscript. Okay, that is n plus 2. So we keep it on one side and we shift everything else to the other side. Okay, so on doing that, what we'll get is minus n plus 1 upon 3 times n plus 2 into a n plus 1 plus negative 6 upon 3, so it will be negative 2 upon n plus 2 into n plus 1 into a n, and then plus negative 2 a n minus 1 upon 3 into n plus 2 into n plus 1. Okay, so once we get the recurrence relation, our job is almost over. Okay, now what we want is we want the values of the coefficients. Okay, if at all we can find them. So we will start by setting n equal to 0. N equal to 0 will give us a2. Okay, so let n be 0 here. It is going to be negative 1 upon 6 a1. Okay, minus 2 upon 2 into 1, so 1 times a naught minus 0. Now this 0 has come because we have assumed that a minus 1 is 0. Note that this is not 0 by letting n to be 0. In fact, this is 2 upon 6 or 1 upon 3. Okay, but because a minus 1 is 0, this is 0. Okay, now the next step that we do is we let n to be 1. So we get a3 now. a3 will be minus 2 upon 3 into 3 or minus 2 by 9 into a2 minus 2 upon 3 into 2 or minus 1 upon 3 into a1 minus 2 upon 3 into 3 into 2. Okay, so this is going to be minus 2 upon 18 or minus 1 upon 9 a naught. Okay, now what we will do is instead of a2 we will write down its formula that we have got by setting n equal to 0. What was that? Negative 1 upon 6 a1 plus negative a naught. Okay, we'll keep all the remaining terms as they are, and in the next step we will try to express a3 in terms of a1 and a naught by identifying the combined coefficients of a naught and a1 respectively. Okay, so if you compute it, for a1 it is going to be 2 by 72, okay, or well, 2 upon 72 will be, oh, not 2 upon 72, sorry, 2 upon 54 or 1 upon 27 minus 1 upon 3, so that will turn out to be minus 8 upon 27. And for a0 it is going to be 2 by 9 minus 1 by 9, so plus 1 upon 9. Okay, so we have managed to express a3 in terms of a1 and a0. Let us see if we can do that for a4. So we have to set n equal to 2 now, obviously, where in this relation. Okay, and if we set n equal to 2 and put value of n as 2 here, we'll get the following: a4 as negative 1 upon 4 a3 plus negative 1 upon 6 a2 plus negative 1 upon 18 a1. Keep a1 unchanged. Replace a2 by the old relation which we even did for a3, negative 1 upon 6 a1 and minus a0. And now use the relation obtained here for a3 and put it here for a3. Okay, so again we have successfully managed to write a4 in terms of a1 and a0, haven't we? Okay, if we do the calculations, for a1 it is 8 upon 108 plus 1 upon 36 minus 1 upon 18. It turns out to be 5 upon 108 times a1. Okay, and for a0 it is going to be negative 1 upon 36 plus 1 upon 6. Okay, so it will be 5 by 36 a0. So you may now observe that for all values of n greater than or equal to 2, an can be considered as a discrete function of a0 and a1. Okay, now soon you'll realize that the arbitrary constants that we expect to get in any second order differential equations general solution are actually a0 and a1. Okay, we'll see that now. Okay, what we have done so far is we have expressed a2, a3 and a4 in terms of a0 and a1, and due to the recurrence relation we can get the values of the subsequent coefficients, okay, in terms of a0 and a1. So let us stop calculating the ans. Okay, let's go to the original solution, okay, the power series. Summation n going from 0 to infinity an into x minus x0 to the power n. This is the assumed power series. What we will now do is we will expand it till the 4th power, okay, because we know what a4 is. I mean, you see, it doesn't mean that we cannot find a5 and a6. We still can, but for the representation purpose, let us stick to the terms till the 4th power. Okay, so it is a0 plus a1 into x minus 4 plus a2 into x minus 4 to the power 2. And what is a2? It is the one in the blue color here. Okay, negative 1 upon 6 a1 minus a0. Okay, this is a2, and this value of a2 has come because of the assumption that a minus 1 is equal to 0. Okay, fine. So that is a2. The next term is a3 times x minus 4 to the power 3. But do we know the expression for a3? Yes, we do know that. Put it there. Okay, a3, it is here in the red color. Negative 8 upon 27 a1 plus 1 upon 9 a0. Yes, negative 8 upon 27 a1 plus 1 upon 9 a0 into x minus 4 cubed. And for this x minus 4 to the power 4, this is a4. Again write it in terms of a0 and a1. Okay, this is the latest. 5 upon 108 a1 plus 5 upon 36 a0. That's a4. Okay, and plus the remaining terms, a5 into x minus 4 to the power 5 and so on. All right. So we have got the power series solution, and what we should now do is we should actually write everything containing a0 as a separate series and everything containing a1 as a separate series. Okay, so let's identify the a0 terms and get them together. Okay, I'm going to use green color for that first. Then in the square term it is going to be minus a0. For the cubed it is going to be 1 upon 9 a0, and for this it is going to be 5 by 36 a0. Okay, so it is a0 times 1 plus x minus 4 to the power 2 into minus 1. Okay. Then for the cube it is going to be 1 upon 9. Yes. And for the fourth power it is going to be 5 by 36. Okay. Now you may consider this to be one of the two linearly independent solutions that we expect to get. Okay. So this is y1 of x in our old notation. We expect the general solution to be c1y1 plus c2y2. C1 is actually the arbitrary constant a0, or the coefficient, the constant term, and the power series inside the bracket is y1 of x. We still don't know the closed form of this. We may never know that. Okay, fine. Let's now identify the coefficients or the terms, the powers of x minus 4 involving a1. Okay, so let me now use pink color for that. Okay, so this is a1 into x minus 4. So it will be 1 into x minus 4. Okay. In x minus 4 to the power 2, we do have it. So minus 1 upon 6 into x minus 4 to the power 2. Yes. In x minus 4 cubed, do we have it? Yes. Minus 8 upon 27 a1. Minus 8 upon 27 a1 is already outside. Okay. Now in the fourth one, do we have it? Yes. 5 upon 108. 5 upon 108. Okay, so this second function that we have got in its power series form is y2 of x. And finally we have got what we desired. Okay, we've got y1 of x and y2 of x. Therefore y is c1 y1 plus c2 y2. c1 is the, I mean, you can call anyone as y1 and the other one will then become y2. So a0 is c1. A1 is C2. Okay. Now at least this example is concerned, as far as this example is concerned, it is very easy to verify that y1 and y2 are linearly independent. Okay, we just make sure that they are not proportional to each other. Okay. Now see, look at the coefficients. Okay, they don't follow any pattern as far as the associated powers are concerned. So we can say that y1 is not a scalar multiple of y2 for any real number r. So we verified that these two power series are, or these two solutions are indeed linearly independent of each other. Okay. Now that's not it. We still are in a position where we have not made use of these initial conditions. Okay, so let's determine a0 and a1. Okay, so here I have produced the same solution once again. Y equal to a0 into y1 of x plus a1 into y2 of x. Okay, now by letting x to be 4, this whole term y2 is going to be 0. Okay, because every term contains x minus 4, and every term even in y1 of x except this term will go to 0. Okay, so we will get 5 equal to a0 into 1, implying that a0 is 5. Okay, now if we take the derivative again by the manipulation theorem, the derivative will be a0 into 2 into x minus 4 plus 1 upon 9 into 3 into x minus 4 to the power 2. So every term in y prime, in derivative of y1 of x, will have x minus 4 in it. Okay, and because we have got x minus 4 to the power 1 here, the derivative now here will be a1 into 1 plus 2 times x minus 4 into negative 1 upon 6 and all higher powers of x minus 4, ensuring that there will at least be 1 power of x minus 4 there. Okay, which means if y prime of 4 is equal to 0, then a1 would be, or has to be 0. And if y prime of 4 had a different value, we would have got a different a1. Okay, so this now gives us a particular solution. This particular solution applies for the initial value problem with conditions y4 equal to 5 and y prime 4 equal to 0. Okay, these were given in the problem. Okay, So y is 5 times y1 plus 0 times y2. Now there is one last point. Okay, we have successfully obtained the power series solutions. We even did the particular solution case. Okay, now we go back to the radius of convergence or radii of convergence of P and Q. Okay, for Q there's no problem, but for P there is, because P is not analytic at 1. Okay, or it is singular, which means our power series solution will be applicable only when x lies between 1 and 7. Okay, but according to the problem, x lies in the interval 4 to infinity. So the obvious question that is now yet to be answered is, does it mean that the solution has a singularity at 7 because it has at 1? The answer is no. Okay, the solution exists beyond 7, okay, including the number 7, but the power series solution that we have got is valid only for the interval which is closed at 4 and open at 7. And this is the thing that we have to write, because the radius of convergence is 3 due to the singularity of 1 upon x minus 1 or p of x at x equal to 1. Okay, so let me put it in this way. Okay, if we consider the function 1 upon 1 minus x, okay, this is defined for all values of x in the set of real numbers excluding 0. Sorry, not 0, 1. Okay, and if we consider the power series expansion of this, then this is valid only for all those values of x for which in the interval -1 to 1. Okay, now this process is actually called as analytic continuation. What do we mean by this? Analytic continuation may be put in simpler words as extending, or the process of extension of domains of the function. Okay, so if we know a function defined by this power series, this geometric series 1 plus x squared, we know that this power series converges or has a meaning only for those values of x in this open interval. Okay, but if we prove by some other means that 1 upon 1 minus x is actually the same power series when x lies between -1 and 1, but 1 upon 1 minus x has a larger domain, in fact it is applicable, it is valid or defined for all real numbers x except 1. Okay, so what we have got is this. Okay, due to r equal to 3, but that doesn't mean that the solution doesn't exist beyond 7. The solution does exist, it just so happens that we don't know what to call it. Okay, fine. Now all these last points that we have discussed, these, even if you don't write them in the solutions, it's okay. What you have to do is you have to make sure that you write what r is. Okay, and if the question is explicitly asking you to mention the region of convergence or region of validity, then you write all these arguments. Okay, fine. So we have now demonstrated and solved successfully a problem, a second order differential equation with constant coefficients, variable coefficients, with the help of the power series method. And this is the end of the session.